Welcome you all for the fourth lecture session in air standard cycle. And today we are going to discuss the diesel cycle, which is also known as constant pressure cycle. The diesel cycle are also known as constant pressure cycle. The diesel cycle is an ideal cycle used in reciprocating diesel engines or compression ignition engines. So why it is informed as compression ignition engines? Because in diesel engines the ignition takes place due to compression of air. So this compressed air has high pressure and high temperature, which is sufficient enough to burn the fuel if it is injected inside the engine cylinder. Hence it is known as compression ignition engines. It is introduced by Rudolf Diesel in 1892, and in Otto cycle, in a petrol engines, the air and fuel mixture is taken inside and is compressed during the compression process. Hence there is a possibility of engine knock or auto ignition of charge, whereas in diesel engines only air is compressed during compression stroke. Therefore this auto ignition is eliminated in diesel engines. Hence the diesel engines are designed to operate at higher compression ratios. So there are four thermodynamic processes in diesel engines. I will show that in a PV and TS diagram. Before that, I will list out the thermodynamic processes. The process 1 to 2 is an isentropic compression process. And process 2 to 3 is a reversible constant pressure heat addition. And process 3 to 4 is an isentropic expansion process, and process 4 to 1 is a reversible constant volume heat rejection process. I will show all those four processes in a PV and TS diagram. Let us draw first PV diagram. So this is the PV diagram for a diesel engine. The 1 to 2 is an isentropic compression process. So the isentropic compression process is the process 1 to 2, PV power gamma is equal to constant, and after compression the heat is added at constant pressure. Process 2 to 3 is a constant pressure heat addition. So heat is supplied in process 2 to 3, and 3 to 4 is an expansion process, isentropic expansion, 3 to 4, and 4 to 1 is constant volume heat rejection, and this is PV power gamma is equal to constant volume heat rejection process. So this is the PV diagram for a diesel cycle, and this is the clearance volume of the engine cylinder, and this is the swept volume, and here the volume is V2, and here the volume is V3, and here the volume is V1 is equal to V4. V1 is equal to V4. So this is the PV diagram for a diesel cycle. Then I will draw the TS diagram for a diesel cycle. In the TS diagram, the same 1 to 2 is an isentropic compression process. So, process 1 to 2 is an isentropic compression process. S is equal to constant. Then 2 to 3 is a constant pressure heat addition. This is a constant pressure heat addition. 3 to 4 is an isentropic expansion process. Then 4 to 1 is a constant volume heat rejection. So, TS diagram is also drawn. Now, in this PV diagram, there are certain ratios to be remembered. Let us start with the first one, just the compression ratio, which is denoted using a letter R, compression ratio, defined as volume after compression, volume before compression to volume after compression. So, that is equal to V1 by V2. Then cutoff ratio, which is denoted using a symbol rho, and it is a ratio of volume when fuel supply stopped to the volume when fuel supply starts or started. The ratio, so we can say V3 by V2. So, here the fuel supply stops and here the fuel supply starts. So, V3 by V2 is the cutoff ratio. And expansion ratio, so this is actually in the process 3 to 4 represented using R suffix E, expansion ratio. So, volume after expansion, it is a ratio of volume after expansion to the volume before expansion. So, in the expansion process, volume after expansion is V4 and volume before expansion is V3. Now, I can develop a relationship between this compression ratio, cutoff ratio and expansion ratio, which is R is equal to V1 by V2. But we can see here V1 is also equal to V4. So, I can write this as V4 by V2, that is equal to V4 by V3 into V3 by V2. So, from the definition, the V4 by V3 is actually expansion ratio V4 by V3. Therefore, R is equal to RE. The V3 by V2 is a cutoff ratio. So, we can develop a relationship between these three ratios. Compression ratio is equal to expansion ratio into cutoff ratio. So, with this information and input, we will start derive the efficiency of a diesel cycle. To start with efficiency of a diesel cycle, we have to develop a relationship or correlation for a heat supplied. So, heat supplied is equal to, so heat supplied is actually at constant pressure process. So for a constant pressure process, the heat supplied is equal to m into, since it is a constant pressure process, Cp into, after the heat addition the state is 3, therefore T3, before heat addition the state is 2, therefore T2. So mCp into T3 minus T2, this is the heat supply, and we have to find out the heat rejected. Heat rejected is equal to, it is heat rejection takes place at 4 to 1, the process 4 to 1. In the process 4 to 1, it is at constant volume, the process 4 to 1, the heat rejection is taking place at constant volume. Therefore, mass into Cv into, after heat rejection the state is T1 and before heat rejection the state is T4. So, we have to write T4 minus T1. The thermal efficiency of a diesel cycle can be defined as a ratio of work done to the heat supplied. So, work done can also be written as heat supplied minus heat rejected, in denominator it will be heat supplied. So, we have to write the formula for heat supplied. The heat supplied is m into Cp into T3 minus T2, and heat rejected is m into Cv into T4 minus T1 divided by the heat supplied is mCp into T3 minus T2. So, by rearranging this expression, I can get 1 minus m into Cv into T4 minus T1 divided by m into Cp into T3 minus T2. So, in this expression the mass in numerator and denominator got cancelled and Cp by Cv is gamma. So, I can write 1 minus T4 minus T1 divided by gamma into T3 minus T2. So, we can write this equation as 1. We can inform this equation as equation 1. And now we are going to develop the relationship between the temperatures T4, T3, T2 in terms of T1. So, let us take the process 1 to 2. The process 1 to 2 is an isentropic process. We know for an isentropic process T2 by T1 is equal to V1 by V2 power gamma minus 1. What is V1 by V2? It is a compression ratio R. So, we can write the T2 as T1 into R power gamma minus 1. So, this is one expression. Expression 2. Then we can write the process 2 to 3. Expression for process 2 to 3. The process 2 to 3 is a constant pressure process. Therefore, process 2 to 3 is a constant pressure process. For a constant pressure process 2 to 3, we can write the expression T3 by T2 is equal to V3 by V2. V3 by V2 by definition it is a cutoff ratio. Therefore, T3 can be written as rho into T2, whereas the rho we can write as it is, but T2 is T1 into R power gamma minus 1. So, we can write T3 in terms of T1. So this is equation 3. Then we have to write the T4 in terms of T1. So the T4 by T3, this is for a process 3 to 4. The process 3 to 4 is actually isentropic process. We can write PVT relationship for isentropic process between temperature and volume. So T4 by T3 is equal to V3 by V4 power gamma minus 1, but we know V4 by V3 is Re, therefore we can write 1 by Re power gamma minus 1. But we know the Re is nothing but, from this relation we can write Re is equal to R by rho, alright. So that we have to substitute here. When I substitute here, I can write rho by R power gamma minus 1. And T3 we know it is rho into R power gamma minus 1 T1, and here I can write rho power gamma minus 1 by R power gamma minus 1. So this R power gamma minus 1 and R power gamma minus 1 got cancelled. So I can write this as T4 is equal to rho power gamma into T1. This is equation number 4. Now by substituting second equation, third equation and fourth equation in equation 1, I will get the equation 1 as efficiency of diesel. In that equation I have to substitute all these. Efficiency of diesel engine is equal to 1 minus T4 is rho power gamma into T1, and T1 as it is we have to substitute, divided by, you have gamma and then you have to substitute T3. T3 is rho into R power gamma minus 1 and T1 minus T2 we have to substitute. T2 is T1 into R power gamma minus 1. So after this, if you rearrange, you will get 1 minus, you take T1 common term, R power gamma minus 1 common term, both. So in numerator only T1 common term, so T1 into rho power gamma minus 1. In denominator you take gamma, R power gamma, it is already available, R power gamma minus 1 and T1 you take common term. So the remaining is only rho here and here 1. Okay. So in this one the T1 got cancelled. So remaining can be written like this: the efficiency of diesel cycle is equal to 1 minus rho power gamma minus 1 divided by R power gamma minus 1 into gamma into rho minus 1. Okay, we can write like this. So this is the expression for diesel cycle. And in this one we can rearrange like this: efficiency of diesel cycle is equal to 1 minus 1 by R power gamma minus 1 into rho power gamma minus 1 divided by gamma into rho minus 1. We can also write like this. In this equation, the rho is always greater than unity. As rho is always greater than unity, the rho power gamma minus 1 by gamma into rho minus 1 is also greater than unity. Hence, for same compression ratio, since this is more than 1, for same compression ratio, we know efficiency of Otto cycle is equal to 1 minus 1 by R power gamma minus 1, right? R power gamma minus 1. This is the efficiency of Otto cycle. And here you have the efficiency of diesel cycle. Since this is more than 1, for same compression ratio, if you see these two, if you compare these two, this is more than 1 and compression ratio is same. Hence, for same compression ratio, efficiency of Otto cycle is greater than efficiency of diesel cycle, right? And then, but as compression ratio of diesel cycle is, or diesel engine we can say, or diesel cycle is more than Otto cycle, the efficiency of diesel cycle is higher than Otto cycle. Okay. So now this is the derivation for diesel cycle or constant pressure cycle. All these results we have to remember what is compression ratio, cutoff ratio, expansion ratio, and this relationship Re is equal to R by rho, and we have to derive the relations between the temperature T2 as a function of T1, T3 as a function of T1, T4 as a function of T1, then substituting in the equation we will get the efficiency of diesel cycle. So now we will discuss a simple problems in a diesel cycle. Determine air standard efficiency of a diesel engine having cylinder bore 250 mm and stroke 375 mm with a clearance volume of 1500 cc. 1500 cc. If the fuel cutoff occurs at 5% of shift volume. Assume gamma is equal to 1.4. So now we will draw the PV diagram. This is the PV diagram. Let us mark the diesel cycle. 1 to 2 is a compression process. 2 to 3 is heat addition. 3 to 4 is an expansion process. 4:1 is a heat rejection process. Now, so this is PV, power gamma is equal to constant, P is equal to constant, heat supplied, and PV power gamma is equal to constant, and here V is equal to constant, heat rejection. Let us mark the clearance volume here, Vc, this is V2, and this is the swept volume, Vs, and this is V3, and this V1 is equal to V4. So with these data, with this information, let us start writing the given data for the given problem. The cylinder bore is 250 mm, so D is equal to, we can write 250 mm, that is equal to 25 cc, 25 cm, and L is equal to 375 mm, that is equal to 37.5 centimeter, and clearance volume is equal to 1500 cc. The fuel cutoff takes place at 5% of the swept volume. Okay, cutoff takes place at 5% of swept volume. So now we have to find out, and gamma is equal to 1.4, it is given, and we have to find out the thermal efficiency or air standard efficiency. We can say air standard efficiency. Assumption, air is the working medium. Assumption, air is working medium. Now we will start giving the solution for the given problem. So first try to find out what is Vs, swept volume. Swept volume, Vs is equal to pi by 4 d square L, that is equal to pi divided by 4 into 0.25 square into so we can write in terms of centimeter. So 25 square into 37.5. So you will get shift pi divided by 4 into 25 square into 37.5. So you get 18407.77 cc, centimeter cube. And what is the volume V1, initial volume, is equal to, and if you look at here, V1 is this volume, so Vc plus Vs. Vn is equal to Vc plus Vs. Vc is 1500 plus 18,407.77 cc. So 1500 plus 18,407.77, you get 19907.77 cc. Therefore, compression ratio is equal to V1 by V2. So V1 is 19907.77, V2 is 1500. So you get divided by 1500 is the clearance volume, it is given Vc, that is equal to V2. So you get now the value 13.2 0.27. Now we have to find out the V3 value. V3 is equal to Vc. So we have to find V3 as Vc plus 5% of Vs, that is equal to 1500 plus 0.05 into 18,407.77. So you get now 0.05 into 18,407.77 plus 1500. You get 2420.39 cc. Now the cutoff ratio is equal to V3 by V2 is the cutoff ratio. So V3 by V2, that is equal to 2420.39 divided by 1500. So 2420.39 divided by 1500 is 1.614. This is the cutoff ratio. Now we have to find out the air standard efficiency. So air standard efficiency, is equal to 1 minus rho power gamma minus 1 divided by r power gamma minus 1 gamma into rho minus 1. So now we have to substitute the values of rho, gamma and r. Rho is cutoff ratio, that is equal to 1 minus, the cutoff ratio is 1.614. So 1.614 power, the gamma is 1.4 minus 1 divided by R value, compression ratio is 13.27. So 13.27 power 1.4 minus 1 and gamma value is 1.4. So into 1.4 into rho minus 1, rho is 1.614 minus 1. So now we have to calculate the values. So 1.614 power 1.4 minus 1 divided by 13.27 power 0.4 divided by 1.4 divided by 0.614 to 1 minus answer is equal to 0.6052. So that is equal to 60.52% is the air standard efficiency. So air standard efficiency is 60.52%. So this is the PV diagram for a diesel cycle. We will solve another problem in a diesel cycle. A diesel engine has a compression ratio of 18. The fuel cutoff is taking place at 5% of stroke volume. Find thermal efficiency of diesel engine. So we know this is the PV diagram. So PV diagram 1 to 2 is a compression process, isentropic compression. 2 to 3 is a constant pressure heat addition. 3 to 4 is a isentropic expansion. 4 to 1 is a constant volume heat rejection. So this is clearance volume and this is a swept volume. Now we will write the given data first. Given data, the compression ratio R is equal to 18. The fuel cutoff is taking place occurs at 5% of Vs. Determine thermal efficiency. So we have to find thermal efficiency. And the assumptions are air is the working medium. Air is the working medium. Therefore, gamma is equal to 1.4. Now, we will solve this problem. Solution. And we know compression ratio R is equal to V1 by V2, and from this 18 is equal to V1 by V2, and from this we can write V1 is equal to 18 times of V2. Now we have to find out the swept volume, is Vs is equal to, and if you look at here, the Vs is V1 minus V2, right? So this is V2 and this is V1. So the swept volume is V1 minus V2. So that is equal to V1 minus V2. V1 is 18 times of V2 and V2 is simply V2, we can write 17 V2. So now we have to find out what is V3. V3 is equal to V2 plus 5% of, that is 0.05 times of Vs. So this is V3. So V2 plus 0.05 times of Vs. So V2 plus 0.05 times of Vs is actually 17 V2. So 17 V2. We get now V3 is equal to, right, and I can write here itself V3. So 0.05 times into 17 is 0.85. So 1.85 V2. So now we have to find out what is the cutoff ratio. The cutoff ratio is equal to V3 by V2. So 1.85 V2 by V2, because V3 is 1.85 times V2. So we get 1.85. This is the cutoff ratio. Therefore, now the efficiency of a diesel engine is equal to, we know, 1 minus rho power gamma minus 1 divided by r power minus gamma 1 into gamma into rho minus 1. So substitute everything, the values what we know, that is equal to 1 minus 1.85 power 1.4 minus 1 divided by r value is 18. So 18 power 1.4 minus 1 into 1.4 into rho minus 1, therefore 1.85 minus 1. Okay, rho minus 1. So that is equal to now So 1.85 power 1.4 minus 1 divided by 1.8, no, it divided by 18. 18 power 0.4 divided by 1.4 divided by 0.85. So after calculation, the value is 0.6387, that is equal to 63.87%. Therefore, thermal efficiency of a diesel engine is equal to 63.87%. Okay. So we have determined the thermal efficiency for the given. We will discuss another problem in diesel cycle. An air standard diesel cycle has a compression ratio of 14. The pressure and temperature at the beginning of compression stroke are 1 bar and 300 Kelvin. The maximum cycle temperature is 2500 Kelvin. Find cutoff ratio and thermal efficiency of the air standard cycle. So let us start with the given data. For the problem, you have to write given data. The compression ratio is 14, R is equal to 14, and pressure at the inlet is equal to 1 bar, and temperature at the inlet is equal to 300 Kelvin. The maximum cycle temperature T max, that is equal to T3, because in a process 2 to 3 only the heat is supplied, therefore the third state will have a maximum cycle temperature. Then find cutoff ratio and efficiency of air standard cycle. The assumptions are air is working medium, therefore gamma is equal to 1.4. I will start with solution. We know T1 and we know R, therefore we can find out T2 is equal to T1 into R power gamma minus 1. So T1 is 300 and R is 14 or gamma 1.4 minus 1. So now we have to calculate the T2. So 300 into 14 power 0.4 is 862.13 Kelvin. So now we have to find out the cutoff ratio to calculate efficiency. The cutoff ratio is equal to, so V3 by V2 is a cutoff ratio. Since 2 to 3 process is a constant pressure process, V3 by V2 is equal to T3 by T2. So cutoff ratio can be found out using the ratio T3 by T2 also. So T3 is 862, T3 is 2500 Kelvin and T2 is 862.13, that is equal to 2500 divided by 862.13, you get 2.9. So this is the cutoff ratio. Now we have to find out the efficiency of a air standard cycle. So efficiency of a air standard cycle is equal to 1 minus rho power gamma minus 1 divided by r power gamma minus 1 gamma into rho minus 1. So we have to substitute the values. 1 minus rho is 2.9, so 2.9 power 1.4 minus 1 divided by the compression ratio is 14, so 14 power 1.4 minus 1 into gamma 1.4 into rho 2.9 minus 1. So we have to calculate this value. So 2.9 power 1.4 minus 1 divided by 14 power 0.4 divided by 1.4 divided by 1.9. So we get the answer 55%. So 0.55, that is equal to 55%. So efficiency of a air standard cycle is equal to 55%. 55%.